All right, good morning. Welcome back. Class number 4 of our wonderful semester so far. Great to have you here. All right, what do you remember from last time? Let's start there. I'll give you a hint. We stopped Bayesian altogether. We went to the other section of the class. Psychometric models. And I believe we left off, here I'll just go ahead. We left off with, we were talking about different types of psychometric models. I think we're on slide 16. Let me get to that real quick. But the bigger picture is this. I wanted to let you know that we have a couple deadlines coming up. Formative assessment 2, remember, free points, just answer questions. That's assigned and is due Monday night, but there's no late makeup for that. It's just, here it is. So, number 2, homework 1 is due tonight. Homework 1, again, is install Stan, the install Stan homework, because kind of hard to do Bayes without something that'll do Bayes with you, for you. So, anybody having any difficulty with homework 1? Yeah. James. Okay. How's this sound? Why don't we talk after class? I can talk to you about it and see how that works. I don't have, without the error in front of me, I'm not really able to troubleshoot it. But generally speaking, if you're following the same steps from the CMD stan R that I had on the file itself, that should go well. But if there's a problem, we can talk about it a little bit later. Okay? You're welcome. Mm-hmm. That's right. Yes, you may want to try that. James, excuse me. Were you able to install Bayes-Plot? Oh, you did. Okay, yeah. So we'll have to take a look and see what's the problem there. Yeah, that vignette seems to imply that CMD stan R depends upon Bayes-Plot, but I think it's a suggestion, which means in R you have to install it separately. That's one of the annoyances with that vignette. But otherwise, I'm happy to. Well, I'll troubleshoot it with you if we have a moment after class, if that's okay. All right. Any other questions? Okay. Uh-oh. So there's a comment about the tool chain in your local machine. That local machine issue is likely. Can I ask, are you running a Windows machine? Yes. Okay. So what you need, if you have a tool chain issue on a Windows machine, there's actually an R installation package you have to install with it. That's called RTools. So if you Google RTools, CRAN, I think that should do it. It'll take you to this RTools site. If you download and install that RTools package or program, what that is a compiler and some other linkers that allow R to build programs outside of it. Do you have? You have that already, and you have the path. All right. Another thing that we'll have to troubleshoot as well. So one thing I will note, not really able to troubleshoot in class here with these problems, but office hours are where this would be great for. So for next homework, which is not out yet, or future problems like this, if you could try to get things run and then come to office hours from 10 to noon on Wednesdays for me, and then Vladimir has 9 to 10 on Wednesdays, and then sometime on Friday, I forget which time. That's a great place to have these troubles shot as well too. Okay, but Lingual, if you want to wait after class, also we can try to troubleshoot that as well too. Okay. All right. Thank you. Other questions, thoughts? No. Okay. Oh, and Vladimir says 10 to noon every Friday, in person where he's at right there, N457, or online with the link that you can find on the syllabus or I think on the webpage itself. Okay. Shall we begin? Lecture-wise? All right. Let me pop this out. We left off at slide 16. You may wonder why I have that excellent memory. It's because I looked it up before we started today. I started about with characteristics of latent variables. I don't have an excellent memory. Maybe at one point I did, but now my head is full of garbage. So, or it's just old. Probably both. Here, what we're talking about, we talked about the latent variable itself. So when we talk about latent variable, it's the thing we haven't observed. It's the construct that we're trying to quantify, the measure. So sometimes we call it ability. Likewise, and I was trying to make the point on this slide that, the bulk of your coursework that you're going to have and the bulk of the studies that you find looking for research are going to have continuous metrical interval level latent traits. And I say interval level, but that's really sort of a weak order. It's not entirely interval when you think of the error that comes with the trait itself. But I wanted to give this slide to you because in the Bayes sense, where we have to choose distributions for some of our variables, right? So remember in Bayesian, every variable, every parameter has a distribution, or if you have an outcome variable, it has a distribution, right? Like the model data likelihood that we talked about last week. I mention this because the interval level latent variables that we normally find often involve a prior distribution that's normal and sometimes standard normal, where the mean is 0, standard deviation is 1. Remember, the hyperparameters of a prior are the parameters of that distribution, right? But that doesn't have to be, right? And because you are looking at a latent variable to use in a study, that thing you didn't observe, you can assign almost any distribution to it. In the world of statistics, if we think of the latent variable as a random effect, there was a small blip of research 15, 20 years ago describing doubly generalized linear models, where the random effects are something other than normal and the data is something other than normal. That could be a situation you have. So here, we may have a continuous variable. It may follow a normal distribution, but it doesn't have to. It's a specification of a prior. You'll see other people in the world have a continuous variable and may use a beta distribution for it. In fact, there's a large testing program in Korea, if I'm not mistaken, that uses a beta distribution. Remember, beta, we learned in our first class, ranges between 0 and 1, right? Similarly, you could use a categorical distribution and have an ordinal level variable as well. This is a diagnostic model, a cognitive diagnosis or diagnostic classification model. You could remove the ordinal assumption and then end up with a categorical distribution that's nominal level as well, right? Heck, well, why stop there? In Bayes, you can do almost anything. You can specify almost anything. Anybody want to have a count latent variable? A Poisson latent variable? You could have one, right? I don't know what that would be. Kind of cool, though, maybe. I don't know. Who knows? Anyway, point being, latent variables, you're often taught, are one form. They're continuous. They follow a normal distribution. I'm here to tell you that they don't always do that. There are large groups of models in DCMs or finite mixture models that don't use normal continuous assumptions, but they still fall into the same framework. Any questions on this idea? Okay. Today, by the way, I'm trying to do a better job not hitting my desk. Like when I'm talking, I hear on the audio of on YouTube, I hear like something like this, or maybe it's my computer or something. I just trying to sign to you with my hands above my head. So if I look crazy like that, it's me trying to remind myself, don't touch the desk loud. I am crazy, but yeah, anyway. Okay. All right. The most common that you'll find of all these variables are continuous latent variables. With a continuous latent variable, if you have taken other latent variable classes, here's the thing. We didn't observe the latent variable, right? We talked about latent variables as saying, I mentioned the last class, I like to envision what happens if you could observe the variable and put it into a model, right? We would have a linear regression or a logistic regression if we could observe a continuous ability and predict how people would score on items with it. But in practice, when we don't observe the variable, if it is continuous, we need to give it a metric. A metric meaning we need to figure out what its mean is, and we need to figure out its standard deviation. All right? The metric, defining the metric is the first step in a latent variable model for continuous latent variables. Categorical latent variables, turns out that metric is already implied by the categories themselves. But continuous latent variables need the metric. Sometimes we call this scale identification. And I will note the metric is arbitrary, right? You can have different settings for what you call the mean or the standard deviation, but still have an equivalent model. Now, that's a model data equivalence. In Bayesian, there's one catch, right? So, for instance, let me back up a second here. How many of you have taken the factor analysis in SEM class? I think most of you have, right? What you learn in that class is there's sort of two methods of simple identification in confirmatory factor analysis. Normally, we set the mean of the latent variable to 0, which is just a constraint we make, right? Point 2, for the standard deviation, there are the two methods that sort of appear largely in research. One is to fix it to 1, right? So we have a standardized latent variable. The other is to estimate it, but we estimate it. When we estimate it, we have to go and fix one factor loading to a value. We usually set that to 1. We call that the marker item technique, marker item identification of factor standard deviations or variances, right? So it's true that if Vladimir decides to standardize his latent variable, and I say, no, I'm going to use a marker item and estimate the standard deviation. If we estimate this method using these models with maximum likelihood, they'll return at the same log likelihood, and they'll be transformations of each other, meaning you can go from Vladimir's identification to mine and not change anything about the model itself. They're equivalent. Now, where we get into Bayes, it's slightly different. And here's why. Remember in Bayes, we always take the model data likelihood and we multiply it by a prior, right? Because we're after a posterior distribution. So it's not always the case when we change equivalencies. Like if Vladimir goes and uses standardized latent variable and I use a marker item to estimate its variance, that means in my model I'm going to have to put a prior distribution on that variance. In Vladimir's model, he will not. And so what that does is it changes the posterior distribution itself. So he and I will not have identical posterior distributions. We may have very similar. In fact, we may even have a posterior distribution where the expected value is the same. But posterior distributions have a little bit more issue when it comes to model identification differences. So what I like to define is when we say same model, we really are defining that this idea of marker item versus standardized factor really comes from a modeling choice. The model data likelihood can be rearranged in different ways to make it work equivalently. But when you put the prior distribution onto it, that changes the posterior distribution. Now, if that bothers you, there are ways to build prior distributions such that the posterior distribution looks a little bit more well behaved. And I will also note that in the limit, right, as sample size goes to infinity, or in our case, as items go to infinity for the person parameter, the posterior distributions will converge to the same distribution. But in practice, you may see different forms. So that's just one little heads up about the Bayesian catch here. Any questions on any of this? No, I feel like I'm boring everybody. What would make this more exciting? Fireworks? Explosions? Does this work? No. I'm waiting for no, I don't think it's going to do it. Anyway, I was hoping to do some of the... No, I don't have my reactions turned on. Here we go. Yeah, I don't think I do. Oh well, it happens. There we go. This is what I can do. Nope, 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 nope. All right. Anyway, let's keep moving here. So let's talk about measurement models depicted by path diagrams, right? Often measurement models, we show a graphical format using what's called a path diagram. In this format, we often have latent variables using circles, enclosed in circles, and observed variables that are boxes, squares, rectangles, what you name it. The path diagram itself, the variables themselves get a shape, right? So the latent variable being a circle, that's a shape. The observed variable being a square, that's a shape. And then we have lines connecting them, directed lines, usually with an arrow. Those lines themselves indicate which variable is predicting another, right? So we'll have a latent variable that's predicting each of the observed variables oftentimes. And I'll have a picture of this on the next slide. So using graph theory terms, a variable in a path diagram, either latent or observed, is called a node, right? These are nodes in a graph. And the lines connecting them are called edges. So here's our latent variable, a node, a circle. And then this might look like a series. If we had 5 items that we measure with this latent variable, this would be the path diagram. You'll note, if you can see it here, there's a small little head of an arrow terminating at each of the observed variables. So that line is said to start with the theta and terminate at the observed y variable. The lines themselves are called edges. All right. So you can imagine the survey that we started the class with last time, where we had the satisfaction with life scale. This might be the path diagram that depicts that measurement model itself. Now, a lot of times you'll see other things involved. You'll have error variances. You'll have all this other stuff there. But I think, to me, the bigger picture is this. The path diagram is a great schematic to represent a very complex model with a picture. But just remember, it's not the same as a model itself. So I always, in my early years when I was extra nitpicky, I would be like, hey, someone would say, here's my model of a path. I'm like, hey, that's not a model, right? Circle plus square doesn't equal triangle. That's not a model. What we end up having here is a graphical depiction of a model. Sometimes more technically, more academic, we'd say the diagram is not isomorphic with the model because not every model parameter is shown here. Not every distribution is shown here, right? We may have different distributions of our y. We may have different distributions of theta, right? If you're not in the confirmatory factor model, you don't have an error variance for each of the items. And so if you have like an IRT model, you wouldn't even have some of the parameters as well too. So the thing about path diagrams is they're good to give the impression of what's going on, but not all parameters can be in the diagram. And there's no indication about the distribution of the variables, and that's what a lot of this class is about, is building these variables themselves. So that's basically our idea. But if we assume the items themselves were continuous, if we go back to this diagram right here, and we make an assumption that each one of these follows a continuous distribution, right? This is the CFA assumption. This is the assumption that we might apply with the 5-point Likert scale, although I would advise you probably not to. Here, what we would end up forming, what that path diagram is trying to indicate, is the variable, the latent variable here, theta, the term that where the arrows start, is the predictor in a model that predicts where the arrow ends, right? So where the edge begins is the latent variable, where the edge ends is the predicted variable. So that means y is being predicted by theta in that case. And as you would normally expect, this would follow a linear regression, a simple linear regression. If we could observe somebody's score, theta, we could put this in a linear regression and talk about how well theta relates to each of the items themselves. So the path diagram actually then is describing a multivariate model. There are 5 regression lines altogether for this 5-variable example, right? Each one of these regression lines has the same predictor. It's theta. But each regression line, and here's a mistake, this should be YP2, typo. But hang on one second here. I'll make a note. All right, fix slide 24 later. Anyway, point being, each of these variables is different. And that means each regression line's parameters are different as well too. So if we were to think of, if we could observe theta, right, this would now be a multivariate regression that we're talking about. How many of you have done multivariate regression before simultaneously in any class? You probably won't see much of that until a multivariate class, because I'll argue that the multivariate model itself sometimes leads to the same result as a series of univariate models. But we have no choice in a latent variable model. We can't take each item by itself and define a latent variable for it. Right? That's unidentified. We have to use a multivariate model for this. So, how are we doing so far? Sort of abstract, giving the abstract idea of what's happening here. But if you were in a linear regression approach, for each one of these observed variables, you could interpret the parameters the way that you're used to, right? So here, beta 0, the intercept, represents the expected value of y, conditional on when theta equals 0. And depending on how we identify theta, if we say its mean is 0, this could be the expected response for someone who's at the average for the latent variable, right? Similarly, our slope represents a 1 unit increase in y per 1 unit increase in theta. And I'm saying 1 unit here because, again, theta not being observed, that we have to define its units. But it's true that if theta plus, so basically what we're saying is the change in y should be beta when theta equals theta plus 1. That's sort of a mathematical idea. As theta goes up 1, y goes up by its slope. That 1, if we standardize theta, that 1 is 1 standard deviation. That's a very understandable unit, almost like a standard unit itself. But it's not always 1. So 1 unit here may be different, as we know. The other nice thing about this, when you're building a Bayesian model, is the following, right? Going back to linear regression, the slope itself is an interesting parameter, right? Because the units of the slope, right? What range would we assume a slope would be? Well, the range, the values of that slope depend on the standard deviation or the values, the scale of the theta. Basically, this slope describes units of y per units of x, right? So in a observed variable context, if you predict y with a variable that has a standard deviation of 100,000, a very large standard deviation, you would expect very, very small slopes to come out, because a 1 unit increase, a 1 standard deviation increase would be 100,000 increase, right? So 1 unit of theta is 1/100,000th of a standard deviation. So that slope parameter would likely have a lot of zeros in front of it. Alternatively, if you consider a theta that might be, or a predictor variable that might have a standard deviation of 0.01, now a 1 unit change would be 100 standard deviations. And you can imagine that slope being very large. And I say all this to you to think about, because in the Bayesian psychometric model, or in a regular linear model phrased in Bayes, we have to give each of these betas a prior distribution. And if their values change widely because of the scale of what we're predicting them with, that standard deviation that we give it, that prior distribution, may not apply to each. We may have to specify a different level of prior for each depending on what we expect the scale of its outcome to be. Meaning, for instance, if I put a prior on this standard normal, all right, where we would expect our belief to say, hey, we think the parameter is close to 0, but there's plus or minus 3 is its sort of 99% of its distribution should be right around 0, and it turns out our predictor variable standard deviation is 0.01, that prior will put a lot of mass in the wrong location potentially, and you may end up with a result that may not work well or fit well. So it's one added constraint when I look at these right here, the thing that sort of pops up all the time, is we have to be really particularly aware of what we expect our parameters to be before we assign prior distributions to it. But that's coming next week. That'll be our next set of slides. How are we doing? All right. The other good news with that is, in the latent variable model, because we can define the scale of theta, that makes it somewhat easier to put prior distributions on all these parameters. Because number one, there's only in this example, there's only a single theta. And for most psychometric models, there may be a handful of thetas. But they're all in a range that we know. We set the scale for it. And it's unlikely that even if we estimate a variance of theta, it's going to be 100,000 or it's going to be 0.01. It's going to be somewhere that's estimable. All right, how we doing? Doing okay? Abrupt jump there. All right, more interpretations of parameters. That error term, the residual variance, is the difference between y and what the core part looks at. Sometimes we call this part the linear predictor, right here. This is the expected value of y. So what we would expect someone's y to be, conditional on theta, is this part. Beta 0, intercept plus slope times theta is our expected value for each score. The difference between our expected value and y turns out to be our error, how far off we are. Just like in linear regression, we would assume that error follows a normal distribution with a zero mean. That is almost always the case. Otherwise, you put a bias on your other parameters. And a variance of sigma squared. That sigma squared variance is sometimes called the residual variance, right? And in a linear regression, we would ascribe special meaning to that. I would talk about that is the value that we look at when we describe how much variance is explained, right? We might fit a model without any predictors. We fit a model with a predictor. We can see how much is reduced, right? We then, if we actually built a 5 regression model estimated simultaneously, that's a multivariate regression where we have multiple outcomes predicted by one or more predictors. And this is where SEM sometimes involves path analysis. If this is a multivariate regression, a whole bunch of other multivariate regressions might follow a similar diagram. In fact, we might have another latent variable, or better yet, this latent variable might predict another outcome, or another outcome might predict it. It's all part of a multivariate regression. It's all part of how latent variable models fit into larger simultaneous equation models in statistics and econometrics as well. All right. So, in the regression model for a single variable, what do we assume about its outcome? All right? So you can sort of trace this out. We can say if theta was, well, let's see here. If error was normally distributed, right? And let's imagine this is a regression where theta isn't latent. This is an observed variable, just to get you that sense, all right? In this model, error is normally distributed. Beta 0, beta 1, and theta are all known or constants. So we know that we didn't put a distribution on these in a linear regression sense. We will in Bayes. In that sense, error is normally distributed, follows a normal distribution. These things don't. So basically, y takes the distribution of error right here. Right? So y's distribution is normal. Here, beta 0, beta 1, and theta are constants, so they move the mean of the outcome. So the mean of y turns out to be what's specified there, as I mentioned, the linear predictor. And it turns out, as error has a variance of sigma squared, the outcome variable also has a variance of sigma squared. So what we're talking about here is that the distribution of any y, sometimes we call this the conditional distribution of y given our predictor, follows a distribution that's normal, where the mean is set by our linear predictor and the variance is set by our residual variance. Right? This is regression ideas, but it still applies. So we say that y follows a conditionally normal distribution. Right? So let's talk about the normal distribution a bit. All right? So when we say y follows a normal distribution with some mean and some variance, that implies a probability density function, a PDF. And as we talked about in the first lecture when we got into the intro to Bayes concepts, PDFs are distributions that we assign to variables. We have to sort of make that subjective choice. We build a regression model where we say error follows a normal distribution. That's our subjective choice, but the result of that is y itself is now conditionally normal. It's a choice. So here, let's talk about that distribution. This right here, this is your univariate normal distribution, sometimes a Gaussian distribution. I'm sure you've seen this distribution before. If you haven't, doesn't it look beautiful? That's just poetry right there. This is, the number of people in the world that have a tattoo of this on them, it's normal. That's literally why it's called normal. No, I'm just kidding. Maybe not the tattoo part, but this right here is what drives the process. The input to this distribution are, well, first of all, pi. The pi is a constant, 3.14. Give me all the decimal places. exp, that actually refers to Euler's number, e, another constant, right? But it's exponentiated with what's in the top. So those are constants. Sigma squared is unknown, mu is unknown, and y we should have observed, right? So we often talk about, oh, there we go. Those three components, the data, the mean, this can be the conditional mean, right? We might substitute mu with what we had on our previous slide, and the variance. So basically, we can use this function in different ways, right? The key to Bayesian methods, or using Bayesian methods, is to know the distributions for each of the variables in the model. So here, if we're going to build a CFA model, and we know the following worked out, we just did the math behind it, that y should be conditionally normal, then we would specify for y a normal distribution where the mean was set by the parameters of the model and the variance was being estimated. That's part of what happens. Now, the other thing I want to note with this distribution is the following. In typical Wikipedia fashion, when we see the distribution, we know, oh, if you give me the mean, you give me the variance, I can tell you the likelihood of y, right? So basically, for a given mean, for a given variance, we can get a normal curve, right? That curve represents how likely an observation y would be. But think of the estimation challenge we have, right? In estimation, what do we know, right? We actually know y. We collect data. We don't know mu. We don't know sigma squared. But it turns out this distribution function works in the reverse direction as well too. Right? If we know y, question from the chat. In the last slide, why is theta constant? I'm using theta being constant here to describe how regression works from a distribution point method. Thinking about regression, we're about to change theta to not be a constant, to let it be latent. So it's more of an example, assuming we have an observed variable, because what I'm trying to build is that psychometric models basically run on observed variable methods, is how I'm trying to define that. I hope that answers the question. So what I was getting to is, if you look at, and actually I just realized I didn't turn on, oh, too late now. All right. Sorry about that. I didn't turn on captions, and I apologize. Here, if you observe y, if your goal is to estimate mu and sigma squared, but it turns out we use this function too. That's what I'm trying to get to. In estimation, we observe a y. We observe everybody's y. We don't know mu. We don't know sigma squared. So part of estimation is forming a likelihood, a joint likelihood, that derives all the data we have. In our case, our likelihood will be set up for everybody's y. And we'll have to use that likelihood function to tell us how likely mu happens to be, or how likely sigma squared happens to be, kind of jointly. So this likelihood function, you normally see it as saying how likely data is given mu or sigma squared, but it's the core, not exactly equal to, but the core of the joint likelihood that works in reverse. How can we find how likely mu is given our data, or how likely sigma squared is given our data? Any questions on that? Yes. Yes, absolutely. The question was about the difference between probability and likelihood. So probability, let's define it a little bit quickly here. Let's say this. In a continuous distribution, like the normal distribution, right? To be a proper statistical distribution, it has to, number one, the area under the curve has to integrate to 1. Basically, that area has to be 1. So what that curve represents is the accumulation of probability, right? And it turns out, if we were to talk about the probability that somebody's y was less than 0, we would take the area under the curve below 0 and call that probability for them, right? Similarly, if we had a discrete distribution, like a Bernoulli, there's a probability associated with the 1 and a probability associated with the 0, and it happens to be their complement, so they sum to 1. Okay? The likelihood is a term used in continuous distributions to refer to not a probability, meaning it doesn't obey probabilistic rules. It doesn't sum to 1. What it does is it tells you basically how likely something is to occur in a relative sense, whereas probability is more of an absolute sense. So if you look at the normal curve and you say, okay, let's imagine you do know mu and you do know sigma, and here we're talking about how likely a y is to occur, the peak of the normal curve happens at its mean, or at mu. So we'd say a y that equals mu is the most likely value, right? And if you were to say relative to another y, let's say a y that's 1 standard deviation away, it's lower on the curve. If you were to compare those two values, you'd say, oh, y at mu is more likely than y at mu minus 1 standard deviation, right? So likelihood does not imply probability, does not describe a probability sense. You wouldn't say it's probably more. You would describe it as a little bit more likely relative to what you saw before, almost like a relative frequency. Now, the last thing about that I'll mention, Vladimir, is that in a continuous distribution, this return right here, this result, is not a probability. In fact, the probability of observing any y is 0. Here's a catch with statistics, by definition, right? So why is that? Because we define on a continuous distribution a probability is an area under the curve, and in calculus, the integral represents that area under a curve. That's how we estimate the area under curve as an integral. If we were to describe the probability of y, that's an integral from y to y. And an integral where the limits are equal necessarily has probability 0. So what we would say is in a continuous distribution, there's no probability at all of any observed y, which you're going to blow your heads about. I got an argument with this about it with a psych professor when I was a grad student. And I couldn't define what I was talking about very well. I still can't. But what does that mean? So what do we define here? So that means when we observe a y, it's actually discrete. And to calculate its probability, we'd have to take some small interval above and below y to get a range for it. Some small epsilon, if you will. Now I'm talking mathematics terms. So likelihood is used when the number returned does not follow probability rules, meaning it doesn't sum to 1 across the space, or it's not defined. Probability is used for discrete spaces or discrete measures, such as area under the curve in this case, or different distributions output itself. Does that answer your question, Vladimir? Thank you. Yes. So the other part of that gets a little weird too. With a discrete distribution, you are calculating the probability of each event in the sample space, right? A Bernoulli has a 0 and a 1. Each of those has a probability, right? That probability is a parameter, pi, or whatever we call it, right? If we flip it, if we say we want to build a joint likelihood distribution to estimate with maximum likelihood, let's say, that parameter, the probability of a 1, right? It's now a likelihood function because the parameter itself is continuous. It may be bounded by 0 and 1, but what that likelihood function is returning is the likelihood of any value of that probability itself, which was the example that we had in our last class, the likelihood of observing a rolling of 1. I guess this was last week. Rolling a 1 on a die is a likelihood. But these are great questions. And this is sort of why I'm talking this class. I'm basically trying to talk about a general look at psychometric models, but taking a statistical turn to it more than you'd see in other classes, because so much of what we do after we get once we get into Bayes and psychometrics is defining statistical values, statistical sets on our parameters, priors and likelihoods and so forth. So it's a very good question, but I hope that answers it as well too. Too much. I always give too much information, I think. All right. Other questions? Moving on. All right, so let's go from regression to confirmatory factor analysis, right? So when theta is not observed, if it's latent, that 5-variable model becomes a confirmatory factor analysis model, right? A CFA model is defined as the prediction of continuous items using linear regression with one or more continuous latent variables as predictors. Now, if you're using this on Likert data, you and I both know that's a tenuous assumption, right? Because Likert data has, every item has 5 options. And a continuous variable has effectively infinite numbers of options. So it's a very big stretch to say I've got 5. Our Likert data with 5 options follows a continuum. But it happens. It happens more than probably it should. All right. Turns out in CFA, we interpret our parameters identically between regression and factor analysis. Right? So if you know regression, you know factor analysis. Right? So theta is not observed in CFA, but observed in regression. So we do have to set its mean and variance. And I did mention standardized factor, and likewise, I'm going to get to that as well again. Each of the model parameters has a different name, but the same meaning. So we might call beta 0 mu, which is called the item intercept. I think you've seen that one before. We might call beta 1 lambda, and that would be the factor loading for an item. We might call sigma squared this psi squared variable, which is now called the unique variance for each item. We can still call it residual variance, but unique. That's variance unique to the item itself. The other catch that we have when we go from regression to CFA, as I mentioned earlier, is we can't just take one observed variable and put a latent variable behind it. It's unidentified, empirically unidentified. We have to have a sufficient number of observed variables to empirically identify the latent trait. What does sufficient number mean? Well, that turns out the sufficient number is for a single unidimensional latent variable, we need 3 items, 3 observed variables to measure it at a bare minimum. If we have a model with 2 latent variables, theta 1, theta 2, one of those latent variables can be measured by 3, and so long as they're correlated, the other 2 can be measured, the other variable can be measured by 2. So you start to get into in a unidimensional model, 3 or more. In multidimensional models, at least 1, 3, and 2, and correlations between factors for the rest. That's the bare minimum, right? You never have to worry about that in linear regression. You can have simple linear regression with one outcome all the time, right? So that's where latent variables are different. This is our 5-item CFA model with CFA notation right here, right? Item intercepts, factor loadings, and unique variances themselves. How are we doing? Questions on any of this? I realize drinking like Mountain Dew and energy drinks probably isn't the best to teach. I'm going with tea today, and just make sure that you see the football's back, all right? So those of you who like the 49ers, you get an A. I'm just kidding. Just kidding. I'm just joking. Just joking. I can't do that. I might think more favorably about you. How's that sound? Better yet, I will put that, if ever you need a letter of recommendation and you ask me for one, I will put that in there. Likes the 49ers, so is a solid person. Just kidding. All right. So, interestingly, when you start thinking about statistics and you start thinking about confirmatory factor analysis, there's this huge disconnect, as I mentioned. We know Likert-type items aren't continuous. In fact, let's talk about why, right? Here, we just derived that y should follow a conditional normal distribution. Well, it turns out in a latent variable model, it's not even conditional. It actually has to be marginal, and you can prove it. And here's why. I'll sketch that proof for you. E is normal. Theta is normal. And if theta has a zero mean and E has a zero mean, which is normally what we define for both of those, the sums of those normals produce a very regular result. Right? So what we end up can show is that the CFA model with a latent variable that is by definition normal leads to the assumption of univariate normal for each of our outcome variables. Not conditionally normal, but univariate, marginally normal. You know the difference between the two, right? Conditionally normal is why if you're in a regression class and someone says, oh, you need y to be a normal, follow a normal distribution, and you start transforming it to make it look normal, I will say that's a terrible idea. Because y is not normal, it's conditionally normal. It depends on what x is, right? Really, error is normal. But in latent variable world, we can show that y needs to be normal. So you can go and look at data and say, does it look could I approximate its distribution with normal? How many of you have collected Likert data before, like a study that or analyzed it? Many of you, right? So let's imagine you do a histogram of each of your variables. If you could approximate that histogram with a normal distribution, what would it look like? Well, let's describe it. It should be unimodal, meaning one peak, and it should be symmetric, right? So that means for the example we had in this class with 5 options for that Likert variable, we would expect for a CFA model to be approximate that data well. We would expect what? We would expect the modal response should be 3, which was neither agree nor disagree. And we should have proportionally similar responses on the higher levels as well. So basically we have a histogram that we could sort of superimpose a normal curve on the top of. Am I making sense? Now, for those of you who've collected or analyzed Likert data before, how many of your variables are like that? Where the center of the distribution is its mode. There's only one mode, and it's symmetric. Have you ever seen that happen? No. Seldom. Seldom. Can't say ever. It's like the philosophy of science, right? We can't prove a null. Santa Claus may exist, right? Tell my child that. And although he knows Santa Claus doesn't exist, he just wants to pretend that he does. So, all right, we can pretend. That's fine. But that being said, all right, so why CFA is probably a bad idea to use on Likert data is that it's most likely not going to fit the assumptions of just using a continuous distribution in general. So that's why there are other types of measurement models that work the same. All right, so I just said that. All right, so what would we do, for example, let's take the further, our example we led class with was a 5-item Likert scale, a 5-option Likert scale, 5 items with 5 options each. And then the second example I took and I made one a binary data, right? Yes, no. What would we do if we had binary items, right? Well, if we took that binary item response and if we had observed theta, again, we're starting with observing theta and then flipping to not observed, and we wanted to predict y that was either a 0 or 1, that's what this notation means, y is in the set 0 or 1, what type of analysis would we use? Well, I'll tell you what we'd use. We'd use logistic regression most likely, or maybe probit regression. Logistic is what we have here, where we take the mean of y in this case, right? The mean of the variable is the probability of a success in a Bernoulli trial. And we apply a link function to it. In this case, this is an inverse link. But in the core of this, right here, actually, this is what I like better. The link function is the logit. The logit is a natural log of the odds of a 1. So you could actually, if you knew what the probability of a 1 was, the logit would be log, or ln, of probability over 1 minus probability. Right? Turns out, why we're doing this is the following. What we're doing, our core of our model is the same. It's this linear predictor. We have theta, which in this case we hypothetically observed, but we're trying to use it to model a probability that exists between 0 and 1. So what the link function does is it takes this probability between 0 and 1, and it converts it into a number that stretches between negative infinity and positive infinity. So the logit is a mapping of probability, 0 to 1, onto the real number line. And why we need the real number line there is that the result of the right-hand side of this equation can be any real number. It can be positive, it can be negative, it can be whatever. Right? So our model itself is for the logit of the mean of the variable. But then we can always back translate it, taking the inverse logit. This up top here is called the inverse logit function. So given our model parameters, we could always come up with the probability again. It's just that we take our linear predictor and inverse transform it from the real number line onto the space of 0 to 1 to get the number that we're after. Questions on any of this? This is generalized linear. This is a generalized linear model. This is why GLM, for me, comes second in our curriculum. You take a linear model class, you take a generalized linear model class, because the combination of those set you up to understand almost all of psychometrics, which is what we teach a lot of in our curriculum, but also a lot of variable analysis in other curricula as well too. So here we interpret the parameters very similarly. However, we just have to remember that our y now is the log odds, not the actual variable itself. All right, so beta 0 is the intercept, which is the expected log odds of a correct response when theta is 0. Beta 1 is still the slope. It's the expected change in log odds when theta goes up 1. This logit changes by beta 1. Right? But you'll notice there's one thing missing in this. Where is the error term? Why don't we have error? Anybody want to guess? Anybody know the answer? The guess was correct, yes. Because what we're end up doing is we're modeling a Bernoulli distribution. And in the Bernoulli distribution, there's one parameter, which is its mean. The variance is its mean times 1 minus its mean. So we don't include the variance in our logit model because the variance doesn't have a spot to go. In a normal distribution, we saw the error variance becomes an assumption as part of the observed variable's variance. For our Bernoulli distribution, we don't have it. Very good answer. Thank you. No nitpicking that time. Well done. Sorry for my nitpicking. That's on me. So Bernoulli distribution is what we use. There's one parameter, the probability that y equals 1. Technically, you could define the probability that y equals 0, but let's just stay away from that for now. This is the PDF of the Bernoulli distribution. It describes the probability that y takes 1 or y takes 0. Now, sometimes, because y is a discrete variable, right? Meaning it can either be 0 or 1, categories, right? Sometimes when you have a discrete distribution function, we call that a probability mass function because the result of it describes probability of a 1 versus probability of a 0. So it's a different terminology than the likelihood itself when we're describing the probability of y. However, as I mentioned slides ago, if we have y, if we observed our data but we don't know what p is, this is a likelihood function because it doesn't return a probability for p, it returns the likelihood of p. So probability is very applied to discrete measures. Likelihood is described to continuous measures. But they both can come from the same function here. But likewise, there is no error variance in logistic regression because the parameter in the distribution, there is no parameter to represent that error itself. And in fact, if you want to think about where an error might be analogously, think of it this way. The further that, if we know with certainty what y will be, there's no error, right? In a Bernoulli distribution, what describes certainty? It's the probability. If that probability is 1 or 0, we know for certain that y will be 1 or 0, right? So error in a Bernoulli or logistic distribution is described by the difference between this probability and its extreme value, 0 or 1. Right? So you can think of error as being present in the model. It's still uncertainty, but it just happens to be that uncertainty is related to its mean as well, too. It's an interesting perspective. So I just said that. So if we were to do this with latent variables, the same thing could happen, right? So last time we changed our intercept to mu. Oh boy, of course. Hang on. I don't know why that happened. Here we go. So last time we changed our intercept parameter to mu, we call it the item intercept. We still call it that here. We changed our slope parameter to lambda. We called it the factor loading. We can still call that here. This formulation is sometimes called item factor analysis. For those of you who learned IRT, it starts to look familiar if you haven't seen it in this way. But actually, this is, in a model data likelihood sense, equivalent to an IRT model. It's just called an IRT model with a slope-intercept parameterization. We call it that way because the loading parameter, the slope, is the loading. It's also equivalent to the discrimination. I'll show that in just a moment. But basically what we can talk about is IRT models may look like this, particularly if you're in other parts of the social sciences, psychology in particular. But they start to look like this in education. And this is one of the features that I mentioned in our last class, where psychometric sort of evolved in different fields in parallel methods. Right? In education, this right here was the core of the two-parameter normal ogive model, 1950, and the two-parameter logistic model, 1967, where those came from. Right? A would be the item discrimination, and B would be the item difficulty. Right? Well, it turns out if you write out each of the equations, if you basically multiply A through this function, you can map the parameters together. You can show that A is lambda from the previous slide, and B is the intercept over lambda times -1. So you literally can transform one to the other without difficulty. Of course, so long as lambda is not 0. If lambda is 0, you're kind of stuck. But where this is important is when we talk about terms, let's not let the field difference from where the model began stop us from understanding. So when I say factor loading, if you're familiar with IRT, I want you to translate factor loading means discrimination. All right? So I might say discrimination. I might say loading. They both mean the same thing. Or I might say slope. That may say the same thing. Slope, loading, discrimination. All of those mean the same thing. Right? The difference is difficulty is not intercept. Difficulty is the point at which a theta has to be to have a 50% chance of answering an item correctly in this two-parameter model that you see here. Intercept represents the logit, expected logit when theta is 0. It's a difference, right? So intercept and difficulty are absolutely different terms. They function similarly. They're sort of a location of different sorts, but it's different overall. And so I just mentioned this here, right here. How are we doing? Questions on any of this? So, a little bit further, way I like to talk about psychometric models is sort of built from this Bayesian idea. When we get into Stan next week, you're going to see that every variable in our model is going to have a distribution, including the latent variables. And if you think about it from a statistics, I need to define a distribution for this variable perspective, then it makes sense that, hey, each of these modeling families we have in psychometrics exist. They have a name, right? If we change the observed variables distribution from normal to Bernoulli, we all of a sudden went from IRT or CFA in normal to IRT in Bernoulli. But the core of what we're trying to do is not different. In fact, if you look at this equation right here, you would say that on the left-hand side is our data, and on the right-hand side is our theory. So theory is always predicting data. It's just that the shape of data may change. right? It may be continuous, it may be discrete, maybe whatever, right? So here, the right-hand side of the equations are almost always the same, particularly when we got down to the logit, right? We had a little subtle differences. There was an error that was gone, not exactly there, but this is the key, is that you already know so much about different modeling families just from the linear models that you know, or generalized linear models that you know. And next in Bayesian, we're really going to specify that because we're going to have to define the distributions for each. But I wanted to go back to one quick point in our slides. So we have a few minutes left here to talk. If you remember this version of the survey I described, where the outcomes were different. Remember that? And I said, can we build a latent variable model for this? And I think you said yes. You may have said maybe said no. But think of it this way. Variable 1 has 5 categories. What distribution would you want to pick for it? How about categorical? We call it that? Categorical distribution has each category. Let's imagine, first of all, actually stop right here. On the right-hand side, let's imagine we have one latent variable, satisfaction with life, right? And on the left-hand side, we have these item response data. So here, a categorical distribution, if we predict it with a latent variable, that goes in multiple forms. That might take to a form of, if we say that there's a common slope, but maybe different intercepts, that becomes what we call a graded response model in IRT, or a proportional odds model in logistic regression. Right? If we allow a different intercept and a different slope, now it becomes a non-proportional odds model or generalized logistic regression in the statistics world, or in IRT we call that a nominal response model. Right? So, but that forms the likelihood for one variable, categorical distribution. With a 2-option variable, we would use a Bernoulli distribution. Right? With a slider bar, we might use, a beta distribution. Right? Just change the limits, make this between 0 and 1, or make the beta have 4 parameters. Right? With this, we might use a count distribution. How many times did you feel happy this week? And with this name variable, well, let's just put that on hold for a second. We have to put a filter onto that to build it in. But the bigger picture, though, is why this works, is that the likelihood function for the latent variable, if you're going to go apply Bayes' theorem to it, which we'll do several weeks from now, we can show that it is the product. If we assume local independence, which is what psychometric models often do, it's the product of each of the distributions of the observed variables, the distribution functions. So here a categorical distribution function multiplies a Bernoulli, multiplies a beta, multiplies a Poisson. That's mathematically allowed. It's perfectly easy to do. You can do that. So why I say this is when I teach these classes and I ask this question, those who are trained, our classes silo this, right? CFA largely describes normal distributions for your outcomes, so all of them look normal. IRT largely describes either Bernoulli or categorical distributions for your outcomes, so all of them look that way. And what I'm telling you is you can combine them. You can have mix and match. You can have some that are continuous, some that are categorical, some that are otherwise, and it still is a psychometric model. It just may not have a name for it. So that's the point of this class, is to sort of put together the big picture ideas for latent variable models themselves. And these features that we talked about, really dwelling on, okay, here's my data, what distribution should it have? Here's my latent variable, what distribution should it have? Is the beginning of building out STAN code or MCMC code of some sort for estimating a model. All right, questions. Do you have any questions for me with any of this? Negative. All right. Then I'll wrap up. It was supposed to be a quick introduction to psychometric models. I made it longer than that. Sorry about that. I hope today sort of did 2 things. I wanted it to talk a little bit about psychometric theory, but really show the generalization of the models themselves. It's a very different class than what you have had in a CFA or an IRT class itself. Put them together, think about it from the big picture. there's other features that are involved in psychometrics that we're going to get to as well too. For instance, anytime you go to a multivariate model, model fit becomes an issue. A univariate model, believe it or not, like a linear regression, we don't talk about model fit in your first linear model class because linear regression fits well. It may not have a great R squared, but in terms of model properties, it fits well. Distributional properties, it's perfect. When you get to 2 variables or 3 variables, you have to decide whether or not you actually approximate your data better, and that's a harder step. So that's going to be part of the end of class as well too. So what's coming up next? Next week we will dive into STAN, we'll dive into MCMC, but we're going to go back to linear regression because as we talked about here, if you can understand what's happening in a linear regression, you can map that into a psychometric model very quickly in Bayes. So we're going to develop how to use STAN, but with models that are very basic, relatively speaking. Simple linear regression and then a little bit more of a multiple regression. It'll help us introduce each of the topics that we need to talk about in STAN, prior distributions, likelihood functions, estimation, and how to make the thing run. And there I hit my hands together, not my desk, but at least I clapped. Sorry about that on the audio. Okay. Well, at that note, with no other questions, I'll stop here. For those of you with questions about... the PDF for the slide is broken. All right, I'll try to fix it. Thank you. I'll try to post it later. And by the way, for those of you, if you want to get a PDF out of the slides, you can always just take the slides, build them, and go to PDF expert mode. But I'll try to do that for you and post it as well, too. Okay. So those of you with STAN issues, just stick around after class. Otherwise, the rest of you, I will see you Tuesday. So thank you for being here. And next week, by the way, next week, be prepared. STAN's going to be its own challenge. It's a fun challenge, but it's a challenge. All right. Talk to you later. Thanks, everybody.